Hello, I am Kush Patel, and this is my lab report on Lab 1 of Physics 2211 at Georgia Tech. This lab uses a rolling cylinder to examine constant velocity. I will first start with the introduction of the purpose along with the physics principles that apply to this lab. Then, I will be moving on to the experimental and computational portions of this lab and their significance to the purpose. The purpose of this experiment is to be able to analyze the motion of an object moving at a constant velocity by comparing the recorded experimental data to a computational model. I predict that the computational model should be a semi-accurate predictor of the object's true motion, as it does not account for every force that acts on the system. The main physics principle that is applicable to this experiment is Newton's second law, which states forces acting on a system from its surroundings cause changes in momentum. To be more specific, the system in this scenario is the cylinder, and the surroundings are everything else in the room, including the table and the air. This law gives us the momentum update formula as shown above. From the momentum update formula, we can derive the velocity update formula. Note that if the net force is equal to 0, then the final velocity is equal to the initial velocity. Alternatively, if the velocity is constant, then the net force is equal to 0. We will also be using the position update formula to track our object as it moves. We start this experiment by recording the motion of a cylinder moving in a straight line at constant speed. We then import that video into tracker software to track the position of the cylinder at set time intervals, which are each frame of the video. This was calculated to be a time of 0.033 seconds. To create our computational model, we update the starter code in GlowScript so that it correctly computes the expected motion. This computational model is graphed along with the experimental data so that way those two can be compared. We must first assume that the air resistance and friction are negligible for this experiment. Also, the cylinder was tracked starting at the moment it was released to ensure there were no external forces acting on the system, therefore ensuring our net force is equal to 0. Our initial position, as shown, is because of the axis orientation of the tracker software. The initial velocity was calculated based on the first two frames of motion in this video. As mentioned, the time value is 0.033 seconds. It is important to note that we assume that the net force on this system is 0, because we did not apply any other force while the cylinder was in motion. This is a summary of our code. The initial values were correctly inputted into the starter code on GlowScript to be used as a computational model for this experiment. We then used the delta t of 0.033 seconds because this was also the time between each frame of our experiment. This way, both this and the experiment could be compared to each other in a fair fashion. Note that this code takes into account for the velocity update formula we discussed and the position formula we discussed to correctly model the motion and the position of our cylinder. On this slide, we can see a graph that showed the experimental position versus time in blue and the expected position versus time in red. Initially, our experimental data followed the model quite well, but it is clear that the model is an overestimate of the real position. This shows that in the experiment the velocity was not constant and there were other forces acting on the cylinder such as friction and air resistance that were not accounted for. If the x-axis was flipped and the cylinder was rolled from the opposite direction, we would see a negative trend with the same magnitude, as the cylinder would be moving closer to the origin in the tracker app rather than away from the origin. It is fair to assume that our model is an accurate predictor of motion at the start of the experiment. Then, the velocity of the cylinder began to decrease as it progressed. While we know that the normal force and the gravitational force cancel out to make the F net 0, there are other forces such as friction forces and air resistance that act in the opposite direction of the motion. These are just a few examples of forces that are not included in our computational model and attribute to the error. Therefore, it is not possible to see how many forces are added together to give a true net force of 0. Thank you for your time.